Yuval, it's all yours.
Okay, thanks, Daniel, and welcome back, everyone. We're in the second part of today's session. This is the standardization proposal part. And the good piece of news is that we already have a note-taker volunteer. Anais, how do we pronounce your name? Anais?
Yes, you said it exactly. It's Anais. So
okay, thanks a lot. In general, I was skeptical initially about the ability to recruit note-takers, but so far, touch wood, so far it's working wonderfully. So thanks again. And without further ado, the next presentation is about a standards proposal titled Commit and Proof Zero-Knowledge Proof Systems. And it's a joint proposal by our own Daniel, Matteo Campanelli and Dario Fiore, and Matteo will give the talk. Let me present him. So Matteo is currently a postdoc at the IMDEA Software Institute, working with Dario Fiore on efficient zero-knowledge proof systems. He did his PhD at CUNY under the supervision of Rosario Gennaro. And yeah, so thanks, Matteo, and the stage is yours.
Thanks, Yuval. I'll share my screen. Yes. Fantastic. Let's try this. Okay. Anybody can see what I'm seeing, what I'm sharing?
Mm-hmm.
Okay, good. All right. I'm going to tell you a little bit about Commit and Proof and what are the challenges and what I feel, and I feel with my co-authors are the next steps in terms of standardization. Let's see a little bit a difference between what we mean with Commit and Proof versus standard zero knowledge. If I have an ordinary zero knowledge proof system, normally I'm dealing with the following problem. Someone's claiming that they know some data on there exists some data that you have not seen, and this data is some property of sort. They know the decryption of something, and they're proving that to you in zero knowledge. In Commit and Proof zero knowledge, we are dealing with a similar problem. You're trying to trust that a certain property is true for some data you have not seen, but this data can be pointed to. And the way we point to this data is basically the commitment. A little bit more graphically, if you assume an interactive proof system of sort, a prover and a verifier interact, and in the end, we hope that the verifier is convinced that P knows a certain input U, such that a certain property RU holds. In a commit and proof zero knowledge system, we can do something on that fashion, only that V receives this pointer to the data, this commitment that I'm representing archetypically as a sealed envelope. The prover or whoever puts it into the envelope, gives it to the verifier, they interact, if it's an interactive zero knowledge proof system. What happens in the end? The verifier should be convinced of what? That yes, there's a certain input U and the property holds for you, but also that this input opens that particular commitment. So giving away, I mean, the only difference here is that in a commit and proof zero knowledge system, we are proving the relation and the opening of the commitment. Where do we need this type of stuff? I'm going to give a sort of loose taxonomy of overlapping situations where you may want commit and proof. One of this is anytime you want to fingerprint or compress some data. With a classic example, let's assume there's a hospital holding a database of sensitive patient data, and we want to do all sort of interesting stuff with this database. For example, we could train some machine learning models that we want to make public. Now, if we want the public to audit the machine learning models, for example, maybe we want to check that they've been trained correctly, right? How can we do this? one way is for the hospital to commit to this sensitive database in a hiding way, and then it could prove that the training was correct. Now, anybody can verify these proofs holding this commitment as a reference. And this is sort of, we use the same commitment for both proofs, which sort of fingerprints the fact that the data they're coming from are the same. Overlapping scenario, commit ahead of time. Anytime, I'm going to make a concrete example, at time 0, at some point, I want to timestamp or fingerprint a certain amount of information, my credentials, for example. They could be information that have to do with my identification, my credit history, whatever. I know in the future, I want to prove things about them, but I don't know what now. Later on, somebody, my landlord asks me for clarifications about my credit history or whatever, and I can prove that to them. And later on, I can do that again. But what I have is a timestamp of some time ago, and I can prove things later. One observation that was made in some recent work is also that we can use commit and prove to gain more efficiency if we apply proofs in a modular way. One way to see this is, for example, in a composite statements of some sort. Imagine you have a circuit that can be semi-discretely cut in two parts. A more algebraic part and a less algebraic part, for example, here. And these two, they share, in the picture, they share an intermediate state U. Now, one approach we could take, we could just prove the whole thing holistically. We take the whole constraint system of the whole circuit and we apply one proof system to it. Or we could take two specialized proof systems, one for the top brick and the other for the bottom brick. And we could use them to prove the whole statement. We should also give to the verifier commitment to the intermediate state that could be used to link the two proofs. And at times this can result in more efficient proof systems. With some more concrete example, for example, I already mentioned anonymous credentials as applications of commit and proof. In blockchains, we could use them for blockchains with privacy properties. For example, if you want to fingerprint the pool of transactions without them referring to anything, or stateless blockchains too. Or if you want to make proofs on data posted on blockchains. And in general, yes, anywhere data needs to be referenced in some way, or privately or succinctly. Okay, so there is this is for the motivation. CP seems useful, but now the question is, why talk about standards and commit and prove? Clearly, CP ZK has to do with zero knowledge proofs, but why would particular care be taken in standardizing CP? And there seems to be a little bit of the point seems to be that commit and prove requires this special type of interoperability on what are we doing the proofs, so the commitments, and how we're proving it. And I'll clarify in a second what I mean. For example, okay. So for example, the type of interoperability we want has to do with what different proof systems are using. I'm committing to some data, and then with two different proof systems, I'm proving two different relations. Now, my system and your system need to know what the commitment is, what format is it? Is it the Pedersen commitment? What's the group? Is it a Merkle tree with masking properties or not? So that's if different systems need to prove the same thing on the same sort of data, maybe they need to know about that. A standard could be useful. And intuitively, they need to know, they need to know what to prove. I mean, the opening also changes in this sense. Another way in which this comes about is interoperability through time. So today I'm committing to something, and maybe I'm going to use a commitment scheme that's going to be legacy later. So the proof systems of tomorrow need to interact with the commitment schemes of yesterday. One way to make sure this works out is to have standards people can refer to. So if we're convinced there's something to standardize, let's talk about what we're going to talk about today, which is what to standardize. This talk, this presentation is a follow-up on something that already we discussed last year. Last year, roughly, we said the same things about the motivation, and there was a rough consensus on, yes, commit and prove seems to make sense in practice, is useful. It seems to be, there seems to be the certain motivation to standardize it. And yes, and we also talked a little bit about how to define commit and prove, and a little bit of some care that need to be taken in defining it. I'm going to talk about it in the next slide without entering the details. And what I'd like to talk more this year is about some more concrete proposals on what to standardize so that we can move on and make some progress. A quick digression on the definition of commit and prove. So, and I'm going to assume that here you know what a NISIC is, non-interactive zero knowledge. And a commit and prove NISIC for a relation R is simply a NISIC for an augmented relation RCP, an augmented CP relation. I'm going to define it in a second. So given R, we can define RCP. How do we define it? Recall a commitment syntax. Here's a non-interactive commitment, for example. You have the setup algorithm that gives you a commitment key, classic commitment, and classic a verify open algorithm of sort that takes everything and tells you this is a good opening or not. What does the RCP do? Well, the relation we want to prove in commit and prove is simply the original relation R and the actual opening works. A little bit more formally, we can define this RCP parameterized by CK, takes an input, the commitment, the actual witness, the opening, and then it does what you expect. It verifies the original relation and then the opening works. That's it. The bottom line of this slide is that commit and prove can be defined as a special case of normal zero knowledge. No more, no less, only the way we parameterize the relation is different. That said, let's move on to what we want to standardize. And first, I'm going to propose that we want to standardize maybe commitments. Why? Because commitments are both the basic data format for commit and prove. So everything the verifier always works with commitments. And they're also the invariant in this augmented relation, right? There's an augmented relation. Any CP scheme is going to prove a property and this opening. What could we standardize about it? Well, first, syntax and security properties of the commitments themselves, and maybe particular schemes. Here we are proposing, in particular, Pedersen to start for a few reasons. One, by the way, I can see that there's chat messages, but I cannot see them. So do block me if there's something important I, the speaker, should look at, but I can't look at it at the moment.
Yeah, that's okay. It doesn't, just discussion of some related work.
The reason why we're proposing Pedersen is there are a few. One, it's fairly simple to define. It's already used in several applications. In the real, it shows up in several places, or either in the form of commitments or in its hash form. It's ubiquitous also in different proof schemes, either explicitly or implicitly. Many efficient proof systems, think of your favorite pairing-based one, they sort of use internally or explicitly some sort of Pedersen hash. And also it's interesting because we have efficient general commit and proof systems for it, either from the AGM and team paper or from the LEGO-SNAR compiler. So to mark a discussion point for later, What do we think about this? Do we want to standardize commitments? Do we want to standardize their syntax and so on? Do we want to standardize Pedersen? Anything else? Moving on. Could we standardize commit and proof constructions? And this is a little trickier, but the ideal goal here is if we have a standard that works in practice, how about, for example, practitioners could benefit from having a reference implementation of sort and see how applications align to a certain, I'm calling API of commit and proof. So what do you commit, what do you prove, and so on and so forth. How do you use it? That said, what could we standardize? What constructions? Here, there's a couple directions one could go towards. One could standardize specific commit and proof schemes or general constructions of commit and proof. I'll elaborate about the pros and cons of both in a second. So suppose we go for specific commit and proof schemes. There are several in literature. There are several schemes that explicitly or with a little bit of tweaking and the security proof, they could be basically commit and proof. Now, not all of them are suitable for all our application scenarios. In particular, commit ahead of time, there's several schemes that are very efficient and they have very good properties, but they tend to have a limitation. They couple the commitment, the type of commitment they're using, and or the commitment key to the specific scheme or relation they're using. For example, in Geppetto, the commitment key depends on the relations you're gonna go to prove. So you need to know what you're going to prove before you commit, which is not always the case. We may want to standardize schemes with this limitation or not. There's other schemes that don't have this limitation. These include something I already mentioned, the HGM 18 paper, Agrawal and others, and Lego Growth 16, which is the commit and prove version of Growth 16 coming out of the Lego Snark compiler. By the way, Lego Growth 16 recently has been implemented in collaboration with Kobe Garken and is part of the ZKProof repo, so it's available in principle. Suppose we standardize a specific scheme. Well, one plus clearly is that it's ready, it's plug and play. Potentially, it's ready for practitioners to use. But how do we choose one? With which criteria? And so on. Suppose, how about general approaches to go from standard, let's call it zero knowledge, to commit and prove? Well, the most direct and naive approach one could think of is the following, right? Suppose you have a general purpose standard proof system. Why don't you encode in the circuit or in your constraint system the relation you want to prove? And in conjunction with the opening algorithm with the commitment key in it. And then you just use the standard proof scheme. Just embed, directly encode the augmented relation, basically. This direct construction has a limitation at times, both in terms of modularity and in terms of efficiency. There is efficient variants of the above. For example, the Lego Snark compiler takes this standard zero knowledge and specialized commit and prove schemes for the verify open algorithm and generates the commit and prove zero knowledge proof system for R. The advantage of this is that it's efficient for certain classes of zero knowledge schemes, including Growth 16 or Pedersen commitments. So if one standardizes a general approach, pros and cons, right? General, we are not, and a plus is that we're not stuck with specific schemes in the long run. We give practitioners and theoreticians, to some extent, tools to build new commit and prove schemes. These general approaches do not need to be inefficient, as mentioned above. The question, though, is a compiler is sort of an abstract idea, right? It's a recipe to build commit and prove schemes. Is this something you want to standardize? It's more theoretical than a practical standard in a sense. Food for thought. So again, marking this point for discussion, do we want to standardize CP constructions? How to choose them? Do we want specific ones, general approaches, and such? Last item I would like to share with you is a little bit more in the longer term. I don't think it's so urgent, but it's interesting. So far we talked about commit and prove, but how about similar approaches? What I'm here calling hash and prove, accumulate and prove, etc. I'm gonna clarify hopefully a little bit in a second. On the left, you see some of the original motivation I mentioned for commit and prove. So compression, fingerprinting, commit out of time, and modularity for proofs. So far we talked how you can achieve that with commitments. You have a witness you commit to it, and then you prove different things using different schemes and so on and so forth. Now you can achieve the same things on the left though, to a large extent, using, for example, a collision resistant hash functions. It's gonna have binding, so you know that if I prove two different things from the same commitment, I'm proving something about the same input, and so on and so forth. What I'm losing is hiding. And also I'm achieving compression. If I need succinctness, I'm getting a variant of this, just a terminology variant in the end is the case of accumulators. Recall an accumulator is a primitive that given a set, it compresses it in a binding way to a commitment that we call an accumulator, if you like, and usually supports efficient membership proofs. Same, we can achieve many of those goals in this way. So the question is, there's opportunity to standardize something that generalizes to these concepts too. And this makes sense also because in practice, we're seeing more and more conversation, both in the more theoretical community, let's say, and in the more real world about how to use some of these tools. And most of what applies to hiding commitments also applies for primitives of this type. Concluding, again, here I'm proposing that we could standardize commitments. Do we want to do it? And to which extent? I'm proposing we standardize commit and prove constructions. How? And I'm suggesting we also think about generalizations of this. What if we standardize something that doesn't require hiding, but has hiding as a special case, so we can include things such as accumulators and hash systems and such. Thanks. That concludes it.
Okay, thank you. Okay, I guess we can start the discussion. So we had some questions during the chat, so feel free to start, those who ask questions during the chat.
So it's not my question, but I like it as well. So there was a question about anonymous credentials. And so my question is maybe how, can you give an example for commit and prove zero knowledge for anonymous credentials?
Daniel, would you like to take this one? Would you have an example yourself?
Sure. I think the idea, right, in identity systems is that there is a lot of data that is generated about a specific person or entity from basic information such as the age, to financial information, to medical information. And all of these data, right, in practice, they're going to be stored in different databases. And so they're going to be committed by different parties, right? Of course, ideally, you would want the kind of the third-party entities to commit to this data and not the specific entity or person, right, that is the owner of these credentials. What happens is that there's going to be ways to prove things about this data, right? And at the end of the day, if you want to prove something, maybe your credit score derived from your financial data. So maybe, I don't know, your visa statements are going to be stored in a specific commitment form and your maybe your transactions or your loans with a loan provider are going to be in a different form, right, or a different commitment. And you would like to have this kind of modularity in order to actually make sure that you can have the interoperability in some sense, right? I don't have the end-to-end use case, right, in mind. If anybody does here, I know there's people here working on identity systems. Maybe that they have a bit more of an idea. But I hope that answers your question.
Yeah, thanks a lot.
So I asked something in the chat which I think Dario answered, but I guess I have a follow-on question. I asked whether Lego Snark and AGM18 required homomorphic commitments, because if we don't require the homomorphic property, then we can do it a little bit more efficiently in the circuit. So that's what the Pedersen hashes used in Zcash sapling do, for example. And apparently we do not need a homomorphic property. So my question, yeah, so does that also extend to when you're computing the commitments as part of the proving system? So I know in bulletproofs, for example, you can basically commit to inputs, and if the commitment is the one that matches the proving system, then you don't have to verify that commitment explicitly in the circuit. You can do it at very low cost. So does that require the commitment to be of a particular form?
Matteo, Dario, are you taking this one?
Maybe let me see if I understood the question. Are you asking like if the commitment has to be in a particular form in order not to put it in the circuit? Is this
right?
The question?
Yes, that's the question.
Yes, I would say so. I mean, in Lego Snark, it is the case. It's it can. I mean, the main point is that there is the folklore construction that says, okay, you would encode it in the circuit, or there could be more efficient constructions than when the commitment has a certain form. You can have more efficiency than encoding it in the circuit. And for example, in Lego Snark, this form is just being a Pedersen-like commitment in the same bilinear groups.
I see. So we can choose a commitment scheme as we're standardizing the proof system that we know is going to be efficient to compute in a circuit, in case we need to do it in another proof system.
I see where you're going. Yeah, I mean, maybe that's, I think, like a related question. I mean, this is also for everybody. Is like whether, for example, like what you said, Daira, is like how much this standardization should be coupled with the specific elliptic curves, right? Because,
right,
for example, the Pedersen hashes and over the sapling curve are very efficient, but I mean, efficient for Snark circuits, but there is a coupling there.
Yeah, and sometimes the proof system will dictate the curve to some extent. For example, you're not going to be able to use the same curves for Halo and for pairing-based system.
Also for maybe like security level,
yeah, exactly.
Maybe a problem.
But in the best case where the curves are compatible, there's still a lot of work to do to make sure that the commitments are compatible.
Right. I do have a question there about what you mentioned, that in Zcash, Pedersen hashes are more efficient, but in some sense, right, the Pedersen hashes are not used as randomized hiding commitments in Zcash. So the comparison would be at the level.
they're actually used as both. So for example, a note commitment in Zcash is a combination of a Peterson hash and a randomization. So it is more efficient than a pure Peterson commitment.
I understand. Okay. The price to pay, I guess, for having it implemented as part of the circuit is that you lack easy interoperability, right? I mean, if you do implement it in the circuit, you need to implement it in every circuit, in every system you use.
Well, not necessarily. That was what my question was trying to get at. I'm not sure if I explained it. If you have, say, one proof system, which is a native commit and prove system, and another proof system that is not, can you make them use the same commitment that will be efficient for both?
Thanks for clarifying.
Yeah, but what about?
I can't think of a scheme for which Peterson commitments aren't efficient. Does anyone have any examples where where a Peterson hash would cause a problem?
It's only a small constant factor between the ones that are optimized in sapling and a standard Peterson commitment on the same curve. So yeah, it's maybe a factor of 2 or something.
So I have a question. So if you want some commitment scheme that will be ZK friendly in many systems, right, or different kinds of systems, then you might want to design a commitment scheme that has a low circuit complexity or low R1CS complexity. And the question is, what do people use, and whether this is something that might be worthwhile standardizing.
I mean, I think the most efficient commitment schemes in R1CS, for example, are going to be based on algebraic hashes like Poseidon or whatever. In fact, that's basically what the paper we're talking about says, if I remember correctly. So we would need to standardize those if we're convinced that they're secure enough.
So again, can you repeat the name?
So algebraic hashes like Poseidon, Rescue, MIMC.
Mm-hmm.
You can obviously get commitment schemes from those in the obvious folklore way.
Mm-hmm.
And
surely those aren't ready for standardization, though.
Yeah,
okay.
So the main concern, there are two kinds of concerns. One is that tomorrow somebody will show that they're insecure, and the second is that tomorrow somebody will come up with something that's both simpler and more efficient.
Mm-hmm.
So what do you think is the more likely concern here?
Yeah, I mean the rate at which proof systems are improving is the latter is quite possible.
Yeah, so basically, I guess that things that we expect them to change in the near future should not be standardized as of now. But there's also this parallel NIST standardization effort, broader, not only for NIZK, trying to standardize basic crypto primitives. So maybe having all kinds of ZK friendly, FHE friendly, there are all kinds of friendliness. We care here about ZK friendliness, so maybe ZK friendly commitment as a way to kind of bridge between different types of systems, including transparent systems, which work very differently and cannot use the Pedersen commitment. So maybe this is something that should be delegated to the general effort of NIST standardizing different types of crypto. I don't know if that's something.
I mean, is there a general consensus that these algebraic hash functions, it's too early to standardize them? I think it's a perfectly reasonable position.
It definitely wouldn't be the first time that a hash function is standardized that is not secure in the long term, right?
That is certainly true.
Yeah, I'm sure that there is some legal clause in the standardization document that says we're not responsible to anything.
I think there's a possibility of a chicken and egg problem here, and that if it's not standardized, no one will use it because it's not a standard. and therefore it also will not get the analysis it needs to show whether it is secure or not. I'm not sure if we would have that for the hash functions we consider standard if they weren't made standard. I guess part of the standardization procedure that was to help in having this competition type scheme to say that, well, we want to standardize something, and we will use this opportunity to select what is secure enough to standardize.
Yes.
I mean, it's certainly worth noting that the other candidates for SHA-3, apart from SHA-3 itself, there's basically no cryptanalysis of them since the competition. Yeah.
Yeah, maybe this should be part of the next NIST competition. These ZK-friendly hash functions, right? It's not part of the current competition, I assume, or is it? I don't know.
So first of all, I think here there's the motivation is incredibly large because of the efficiency gain. So I think already both Coda and Filecoin, they've shifted to Poseidon or MIMSI or one of these. So the motivation is large enough to use them also without them being a standard. I've understood that there was this big conference in Paris with these sort of hash experts like half a year ago about these snark friendly functions, and they basically what they said is it's too early to. They need a few years to.
I mean, the Halo paper uses Rescue, but Halo doesn't really depend on Rescue. It's just the most efficient thing that we could use at the time.
But for all the R1CS, right, I mean, this very much relates to the Lego Snark paper. I mean, right, you always, like, in all these R1CS snarks, like Pinocchio, Grot16, there's some group element that the verifier computes from the public input. And this group element is sort of a Peterson hash of the public input with certain like special generators, and you can, that's what this Lego Grot or whatever thing it's called in the Lego Snark paper, it's what it's called. You can use that as a commitment. Like, instead of giving the public input and having the verify, you can just use that as a commitment, and then you can immediately use it inside the snark without having to like. So yeah, so that kind of thing for the R1CS stuff, I think it's more efficient than using any hash function. I think.
Yeah, and we're only talking about maybe a factor of 4 or 5 between Pedersen commitments and these algebraic hashes in R1CS. So it's not as though it's.
No, but my point is, when you do it this way, like they do it in this Lego Snark paper, then you don't have to actually.
Oh yeah, you don't have to do that in a second anyway.
Yeah.
And we also need to keep in mind that there is the hardware acceleration projects that are doing modular exponentiation. Maybe that does help when in the instance of having the Pedersen hash encoded in the circuit itself. Right?
It's also worth pointing out that Plonk can do Pedersen hash commitments really efficiently.
My understanding for Pedersen hashes is that they're really like efficient and good inside circuits. But if you happen to be in the situation where the reason you're using commit and improve is to like squish down the verifier's input in order to make the instance smaller in order to make the verifier fast, actually computing the Pedersen hashes would be about as slow as just plugging in the instance. So they wouldn't gain you anything. Whereas if you were using one of these algebraic hashes or SHA, then you would be able to get your verifier much faster by compressing your instance.
I have a short question.
That also depends on the proof system.
Yeah.
I have one more question around this, maybe to close this topic in some sense, because we also should move forward. But could the sort of a scheme or Lego Grot16 or Lego Snark in general, could it be generalized in order to both theoretically and practically, right? Maybe practically it's about the APIs, but so that different, right, commitment schemes could be used in the span of time in some sense, right? I mean, I believe the answer is yes. That's also, I think, one of the features, right? That you can commit data with different commitment schemes, but use the same relation, right?
Wait, how would you do that?
I mean, I'm asking really whether it could be abstracted so that you could just replace the commitment scheme and the relation would be, okay, maybe not the full relation, right? But
so what you could do is have a specialized proof that does nothing but prove that
the commitment is
the opening of a commitment using one scheme is the same as the opening using another scheme. So you can bridge between schemes like that.
Right. That's actually what we do in the accumulate and prove paper.
Okay.
But between a commitment to RSA and a commitment to a elliptic curve group. Yeah, that could be something actually if we see that it's really needed in some sense for future updates or something like that.
But maybe, I mean, to wrap up, I mean, my understanding of this discussion is that there is interest in like both directions. Also, like there is interest in maybe commitment schemes that are good for instantiating the generic construction, and by generic construction I mean the one where you encode things into the circuits. And there is also interest in maybe more dedicated in maybe considering schemes for more dedicated constructions. And these schemes would be maybe the classical Pedersen commitments. And one more thing I wanted also maybe to ask is, you know, because I believe that Pedersen commitments are should be a candidate because they are used in so many constructions, and also in some constructions that you know don't have anything to do with snarks, like sigma protocols, classical sigma protocols. And I also wonder whether they're already used in some industrial products. I remember in the last year workshop, Angelo De Caro was mentioning something about, you know, about that at IBM. So, you know, that what I would.
That's a good point. Are there already standards that that standardize Pedersen commitments? I don't know.
I don't know.
Can I ask? Can I say something? Dario?
Yeah.
One question also is like, if you think of standardizing Pedersen commitment, the thing is that, for instance, if you come to a vector using Lagrangian evaluated at a certain point, you can also think of it as a Pedersen with another key distribution, no? So the question is, when you think of standardizing this, do you want to standardize also the key distribution or not? Does it make sense?
It's a good question. It's no, it makes perfect sense to me, and it's a good question. Yeah, I don't have an answer, but it's. I mean, there is a difference, maybe like, you know, that, and the difference is essentially the same difference that you have between a structured reference string and a random reference string, because like the very classical Pedersen, you can instantiate it with purely random group elements, whereas the other ones would require trusted setup.
So one suggestion I would make is that we should at least standardize the terminology, because my feeling is that there's at least 3 different types of commitments and different discussions people were talking about different ones, and I'm not even sure everyone was aware about which one the other person meant. So I think just standardizing the terminology for those 3 different ones, like I think one of them is the scheme specific one. The other one is kind of the external one, which is part of schemes, but can be part of many schemes, like a Pedersen commitment with random basis. And the third would be the kind of the one for the generic commitment scheme that is kind of embedded in the circuit. So these 3, I think if we manage to disambiguate those 3, so we always know what we're talking about, that would already be a great success.
That point about the the distribution is a very good one, because on certain curves, you can use the endomorphism to do a more efficient scalar multiplication if you change the distribution. Halo actually uses this.
Okay, so I guess it's time to move to to a different, slightly different topic. How about use cases? Can someone point to specific use cases they have in mind for commit and proof? Maybe something that is different from the application scenarios that were presented. Any use cases that motivate something that's slightly different than the way we typically think about commit and proof?
I personally would like to hear, like, maybe more specifically from someone who's using commitments in some scheme with zero knowledge proofs. Maybe they're not using the commit and proof paradigm yet, but maybe it could be a basis for a discussion as to whether it would be actually useful. So anybody here, maybe someone who hasn't spoken, that would be a good chance as well. We want to encourage everybody to participate.
How about okay.
Actually, I wanted just to add one thing, that maybe it's not direct application, but it's quite similar. Maybe we can think about it. I mean, in this new paper that I mentioned, it will come. So basically, we are defining a relation and encryption of, let's say, some witnesses. But here exactly, they are committing to the witnesses. And then they want to give a proof that, for example, we know this witness in this commitment. And in different scenario for achieving black box extractability, basically we are doing the same. So what I want to say is that in UC security also we are committing to the witnesses because we want to give this possibility to the black box extractor of UC simulator to be able to extract these witnesses. So basically what I want to say that maybe this commit and proof in cases that you want to achieve black box extractability, so you can commit to the witnesses, and then you will give this possibility to the extractor of, let's say simulator of UC simulator to extract the witness from a corrupted parties to simulate them.
I want to comment something on that. And it's something that actually we, we try to clarify on the notions of commit and proof in the Lego Snark paper, but it's also partly in this proposal. So we observe that it's actually true that many schemes have a commitment of the witness as part of the proof. What is not always the case is that this commitment is what we say reusable. So essentially what the main distinction is that you create this commitment with some randomness and you create this along with the proof. And it's different from when in real commit and proof, you should just take this commitment as input, as the statement essentially. So you have in some sense no control on the randomness that is used to generate a commitment. So yeah. So I guess that times when you encrypt the witness in the for the sake of extractability, typically you generate that encryption along with the proof.
Yeah,
and is that necessary for that construction?
You can send encryption, let's say ciphers in advance, and keep the proof. And later, whenever you want to open, you can reveal the proof. I can give a paper reference to that one. Basically, we generate a ciphertext, but this proof gives a proof that I know the witness encrypted in the ciphertext. But now you can first send the ciphertext, and finally, whenever you want to open, you can send the proofs. I agree that it's not as flexible as this commit and proof system because it's a very particular case. You cannot maybe do later new proofs for the same commitment, but maybe you can re-randomize the proof. I use this idea in building black box extractable snarks. But later I saw Carla's paper that they used encryption of, let's say, LGAML in PKC19, that they are committing by LGAML and then giving a proof for that one. Then I observed that, okay, this is basically equivalent to achieving black box extractability because we are committing to witnesses by encryption. And then we are giving a proof that I know the same witness inside the commitment. I agree that in most of applications, we have already this commitment, like as in Zcash, we have committed to coins on tree, and then we generate a proof that we know this coin.
Question is the current commit and proof functionality the most expressive one could hope for, or is there an even stronger type of primitive that you could imagine being useful?
I would say that this commit and proof is more flexible. I saw the definition. I support this one. Just I wanted to say that in some ideas, maybe this proof also can be more efficient by snarks. We will see in this tiramisu that I mentioned about it, because we are just committing to witnesses and we are using a simulation sound proof. We already have some simulation sound proof from Grat and Mahler from Crypto 2017. So this has just 3 group elements. So basically, if you have linear, the shortest, I mean, in that scenario, we show that CPA secure encryption is enough. Basically, LGAML has 2 ciphers. So basically, you have 2 ciphers commitment and you use a simulation sound proof of this LGAML, this Grat and Mahler. And you basically have a commit and proof system, but it's very simple and not as flexible as this one. I wanted to say that in some cases, I wanted to mention that we can achieve so restricted functionalities of this commit and proof with the snarks as well.
So what do you mean by restricted functionalities then?
I mean, in that case, we are limited that these ciphertexts and proofs are generated together. And but just you want to send ciphertext in advance as a commitment and keep the proof. But later, this proof basically proves that I know the commitment, but I haven't thought about it, but maybe we can use this randomization of proof and giving the different proofs for the same commitment. I maybe can share a paper that I'm talking about, it just maybe to make it more clarified.
Yeah, can we put a link to that paper in the notes?
So I did this work, I mean, on constructing black box snarks, but I would say just if you look at the page, okay, in page, you can find in page 12, we have C's encryption of witnesses and with X and witness belong to the language or L. If you open to page 12. Basically, in that paper, I was trying to just achieve black box extractability in Grat-Mahler ZK snark. But finally, I saw that if you look at the proof, it is just a commit C and with a proof, I mean pi prime in prover, output of prover. If you look at its pi prime, and pi prime is C plus pi. And this C basically is a commitment, it's a ciphertext. And this pi is a proof for that ciphertext, that ciphertext includes the witnesses. Then I observed that, okay, we can send this C in advance, it would be a commit. And then whenever you want, you can reveal this pi. But I know that it's not as flexible as this definition of commit and proving, because I think in this scenario, it's more flexible. But since we have now the idea of updatability in snarks, so maybe Carla's question that asked about the standardization of this distributed key generation can also be this updatable setting. I mean, we can have updatable key generation for commitments and the snark that you want to give a proof or NISC that you want to give a proof.
Okay, thanks. Just a random question. If we want, say, a timed commitment, that I give you a commitment that everyone can open in a few days and prove thinks about it. How does this, is this a useful functionality, right? To have a timed commit and proof? Timed commit.
Like a verifiable delay function, or
yeah, a verifiable delay function is related, but it's a simpler primitive. Timed commitment, it's really a commitment that is kind of
more like a hash time lock or something, right? Something that's
yeah,
I think the language.
It was called timed commitment. This was an old paper of Bonnen. Oh, just a commitment. The goal was to do a coin tossing, right? That to get around the fairness problem of coin tossing. But it's something that you could imagine being used in situations where, I don't know, I make some prediction about the future, or make some proof of a sanity check that whatever I committed to is indeed something that's meaningful. And then, you know, in 10 days, the whole world can see it. So can you imagine this being useful, and can this be somehow, of course, this calls for different types of, you know, maybe you can use the existing commitment schemes and make them a bit weaker by releasing some extra information.
So does that functionality make the verification more costly? Is it just the proving that's?
No, it's just that the commitment scheme is, you know, if you could give some hint that allows you to open, I guess it has to be a binding commitment. So this conflicts with succinctness. So commitment is binding, is like statistically binding, because it has to contain all the information. So yeah, it's like I commit some kind of a prediction for the future. Zero knowledge makes perfect sense in this setting, because you want to check, you know, that my commitment is meaningful in some sense, and yeah, or more broadly, you can think of commit and proof as some kind of committed, like an ongoing computation. You have a CPU and it wants to run, and you basically want to commit to the state of the CPU. You can think of a general purpose computation being done in a commit and prove way. Is this something that's useful in some scenarios?
Yeah, Yuval, this is Abhilash here. We have been working on similar technologies, especially from the physical world, proving it in the, keeping the proof in the virtual world and then getting it back to the physical world, especially things like judiciary and where time commitment is very important. At the same time, privacy has to be established. At the same time, hiding and binding also needs to be there. In case of crime and judiciary, I think this is very, very important. I will certainly connect back with you with more information, but this is really interesting, and at least I think the terminology is part we should standardize. I think that's very important.
Sorry, carry on.
Go ahead, sorry.
I was reminded of a detail that's important when you're defining Peterson hashes. The generators have to be independent, and they have to be verifiably independent. So the ones that we use in Sapling, for example, we derive the generators using Blake 2b and a hashing function to the curve. So it's as important to standardize that as it is to standardize the rest of the function. It's a detail that most papers about Peterson commitments leave out.
Mm-hmm.
I actually want to strengthen what Dario just said. There are a few implementation of Peterson hashes that differ in this, and this is very annoying for interoperability. We can't today make proofs from two different proving libraries that implemented this differently, and this is very, very annoying for us that are implementing this. And maybe just to say another sentence on how it also relates to algebraic hashes. So they also have constant that need to be derived, so that's also good to standardize.
Yep.
But even worse, some of the algebraic hash function papers omit the part where you move from a random permutation to a hash function. And some people did it differently. Some did it with a sponge, some did it with in another way with a duplex sponge, so some did it with a Miyaguchi perennial, and like many different ways. So this is also would be nice to standardize.
So very good.
So just to be clear, like that I understand, the issue here between having the different implementations is maybe both at the level of the generation of the generators and at the level of which elliptic curve is used, right?
Yes,
or only one.
And also in the case of these hashes that require other parameters. So for example, the MDS matrix in Rescue and Poseidon, it isn't always specified. You can look at the reference code, but we don't want to do specification by implementation.
Right.
Can I contribute something?
Yeah.
So we are looking for applications of this commit and proof scheme, but I would like to, I think maybe it's interesting to think it the other way around. Like, why isn't everything a commit and proof scheme? Because actually, I don't see what is the point of what do you lose by this formalization? And to give an example, with the Grossa high proof system, there is the standard formalization, and then there is this other paper by Groth in 2014 where he formalizes it as a commit and proof, and nothing is lost. You only gain functionality. So my polemic question is, why don't we do anything else but commit and proof?
I think that's a really excellent point.
Yeah. I think maybe the implicit understanding that it's typically the case that every primitive has a more general version of the primitive, and the question is, it's really a question of balance between simplicity. So I think there's an implicit understanding that most constructions extend naturally to the commit and proof setting, but yes, so that's a good question whether this should be the main standard.
So I think that if you were to standardize both the straightforward version and the commit and proof version, then you're not getting any simplicity in the standard by that, because it's as complicated as just standardizing the commit and proof.
So the question is, how come people up to this point? So my question is, in what portion of the applications of ZK is the commit and proof, like applications of snarks, is commit and proof something that's universally used, or it's used in
I think almost all of the applications I've seen could benefit from it. They don't necessarily use a scheme that provides it natively, but there are very few applications that don't use commitments and that couldn't benefit from this.
Yeah, I mean, the basic idea for that, right, is this idea of garbage in, garbage out. Like, if you don't have a way to sort of make sure that your input data and witnesses are integral data, right, that there's actually somewhere that you can reference to it, what are you really gaining from zero knowledge, right?
So the question is whether the commitment is part of your system, or the commitment comes from blockchain, or from some PKI, or from some external infrastructure that you don't have control over.
So sorry, carry on.
Yeah, I was saying that actually is one of the main points we're raising in the proposal. Then we believe that the commitment should not depend from the proof system. Especially if you think that you want to achieve interoperability, or like, use this commitment in 10 years or something like that.
Or rather,
then you cannot tolerate such dependence.
I'm not quite sure I put it that strongly, but you certainly need to have the option of using a commitment that is not tied to the proof system.
So maybe I'm missing something, but it seems to me like the obvious downside of using commit and proof is if you have a relation which takes very large witnesses, which it does very little with, then verifying the statement size for a commit and proof scheme will be artificially inflated by the fact that you have to do a bunch more on the commitment side than the actual.
So you don't have to commit to all of your witness?
No, I mean, it's just more general. Commit and prove is a strict generalization of proof. So if you don't want to use the commit aspect, you can always deal with it. It's really a question of balance between simplicity of syntax and usefulness. I guess that's a very interesting point, and it may be very suitable for an offline discussion, whether the main definition should incorporate the commit and prove, or this should be an add-on or an extension.
I'm strongly in favor of the main definition including it, because I think, so there's some, if you're trying to teach or if you're trying to present a new proving system, there's some pedagogical advantage in it not being a commit and prove system. But if you're trying to standardize something, that's a different situation. And I think it's worth paying the cost of standardize something slightly more complicated, and just paying that cost once for, rather than having to add the commit and prove functionality as a separate step.
Good.
If you had a generalized lifting transformation, which I think I don't have a specific example of one, but I'm sure they exist. Would that not be simpler than writing out your lifting transformation for every single scheme?
It depends whether the lifting transformation is as efficient as you could get by a dedicated commit and prove scheme.
Okay, that makes sense.
Or maybe do you have a high-level understanding or some abstraction that explains why certain, say, algebraic or pairing-based proof systems lend themselves naturally to the commit and proof extension? Is there some kind of an explanation? You're saying, okay, we can make it all work with Pedersen. Is there some kind of a higher-level explanation of why? Or if you look at the future systems, do you have some rules of thumb, not a fully general way of lifting, but something that says, if the proof system has a certain structure, then we can make it commit and prove without paying.
I mean, I don't think there can be a general lifting that works for all proof systems, because systems can be very different. If you consider hash-based proof systems are not going to be compatible with a discrete log-based.
What I was asking is, if you look at discrete log-based systems, can you give a quick recipe or explanation of some way of specialized lifting, so lifting that applies to a class of constructions?
This is the theorem that we prove in the Lego Snark paper that Matteo was mentioning.
Okay.
I mean, for curiosity, the idea is that if we define a class of schemes that we call commit carrying. So essentially we're saying, like, there is an element of the proof that you can pinpoint, which is a sort of maybe not reusable commitment of the witness.
Mm-hmm.
And then you just need a commit and prove scheme for just verifying the opening of that element.
Mm-hmm.
And then, like, for all pairing-based schemes, these you can essentially show that you can do it efficiently if this opening is just very computing a multi-exponentiation.
Mm-hmm.
So being able to describe if for the sake of argument we did choose to standardize the commit and prove variants, and being able to describe them all as an instance of this general lifting would be very helpful for analysis and understanding.
I mean, the question that we wanted to pose here is, like, whether it makes sense to standardize like some sort of generic lifting transformation, being it the one, specific one, or maybe the one through the circuit to embed the commitment in the MP language supported by the proof system. Is it something that should be done by a standard or not? I don't have an answer to this, honestly. I don't have much experience with standards.
I
But
think
it looks a bit awkward to me that the standard actually standardizes sort of theoretical compiler.
so. So it's kind of something that doesn't necessarily go in the standard itself, but goes in a rationale. I don't know. Is there a place to put such rationale?
Theoretically, yes.
Okay.
Maybe this is a good point of transition in some sense to kind of think about this, the next steps of the working group, and how would such a standard look like, right? One of the things we've been thinking of, I guess, is that an actual standard wouldn't look like a paper, right? Anyone who's worked on a standard or actually used a standard that has read one, right? You have all these terminology, should, shall not, etc. That's one thing, but then there's also a bit more lack of theorems, and you have much more explicit, kind of to the point sections, right? And I think
I'd like to see all of the theorems in this rationale.
Right. So in a rationale, maybe as an appendix to this standard, right? But yeah, I think what would such a standard for commit and proof actually constitute, right? I think we're clear that the definitions would have to be there. It seems like in terms of motivation and usability, well, we should probably pan out a concrete application. That's at least my opinion, so that the people can actually see how it is used, more practically speaking. There should probably be a reference implementation, right? We like those kind of things. That is also like at least tested or reviewed. We've spoken about the concrete commitment schemes. So that's, I think, something we do agree on, most of us here, at least those who have spoken. And if you haven't spoken and you disagree, please do speak up. Yeah, I think, please say what else would go in such a standard, specifically for commit and proof, right?
It should be compatible. If we have a separate standard for proof and for commit and proof, they should obviously be compatible.
That's a good point.
Yeah, definitely. I mean, one thing we didn't really get to talk about right now is exactly that, right? There is no actual zero knowledge protocol that is standardized. And, it was mentioned that it is a bit too early maybe to standardize, given the evolving nature of these schemes right now. And as such, maybe...
we have the NIST people helping us, right? So they have a vision here, right? And they also...
So I think there's a good case for just picking something like GROT16 and writing out how that would be standardized. And even if by the time we finish, no one is using GROT16 anymore, that's still a useful exercise.
That's a very valid point. I like that.
I also agree.
But what template would you follow? What is the recommended template to follow when doing such a thing in terms of how it's presented and?
Well, that's what we've got to decide.
Yeah.
I don't think we can just wait for the ideal proof system, because there's no such thing and it's moving way too fast. We would end up with something in 5 years, but that's too late.
Yeah, I think in terms of template, we could start by looking at what the ITF does. Like, we don't need to reinvent the wheel everywhere. Of course, the idea of working groups and this charter comes from there. It's not something we came up with. And same for the format. If we start looking at what a format for standards look in ITF, we could definitely imitate that to the extent that we need to adapt to our schemes and proposals. I encourage everyone here, especially those that have contributed and have something to say, to join the working group. because this and other ones that may interest you, because we are going to move forward. We're going to have follow-up calls, right? We're not going to get all the community involved necessarily, so make sure to keep updated that those ad hoc meetings happen. So yeah, that's I guess that was my main point to make.
I had a very quick question. Is there any interest to standardize also some older proof systems like compositional sigma protocols, which are used, for instance, for these algebraic maps that are being used right now for Signal, or even for Pedersen commitments? They could be useful.
That's a very good question. I mean, we've definitely hoped to look into that, to have discussions around that. Unfortunately, there is, I think, only one proposal that is related to that. I believe it's not a proposal, actually. It's an SOK, and we do hope to see these coming up, right? I mean, if anybody here has written such papers and would like to submit or written an implementation, that's also a good place to start.
The graduate book of Bonnet.
It would be useful to just have a standardized way of doing the things that are in, the Kamenisch-Stadler paper, like proofs of same discrete logarithm, all of the stuff in there, because they keep coming up in new protocols.
Yeah, definitely.
And
okay, let's keep that in mind.
Oh, yeah, sorry. Okay. By the way, about templates, I've been following the BLS signature template, or BLS signatures standard. That's spec that's being done in the IETF. And maybe that could be helpful as a template because it's close to being done. So that's a unique feature.
Yeah, if you could share the link maybe, Kobe, that would be
definitely.
very useful. Thanks.
Okay, I guess that we should end it officially in 2 minutes. So does anyone have any concluding remark to end this meeting in a bang or whatever? Mary, would you like to conclude? You started.
Sure. Thank you very much, everyone, for being here and contributing and participating in standardizing commit and proof systems and lifting transformations. Do take part in the working groups. I've just joined them myself. It's very easy. You just click the link. And yeah, thanks again. Maybe over to Daniel or
Yeah. Sure. I would like to again thank the speakers. So thanks, Matteo, thanks, Berzad, and the moderators. No one has thanked you guys. So thank you, Yuval and Mary. Great job. I think this was very nice.
And the note taker.
And the note taker, yeah, nice.
Yeah,
and Markov as well.
Both note takers, yeah.
Right. And thank you everyone who contributed. So Yao, are there any last points? Yes, I guess the feedback form. So we are going to send you all a feedback form. Or it's already in the links page. Please do send us feedback. This is the main drive for improving these discussions. And we would like to see you all on Monday at 3 p.m. UTC.
On the dot.
On the dot. I'm going to stop recording now. Anybody who wants to stay can stay.